Locally linear embedding, part 2. Now we'll look at the derivation and the various steps of LLE. So briefly, just to recollect, this is what we do in LLE. For each point xi in the high-dimensional manifold, we construct a neighborhood, a k neighborhood consisting of the k nearest neighbors of each sample xi. And then we find out weights so that this sample point xi can be expressed as a linear combination of its neighboring samples. Xi is approximately equal to summation wij xj. And then once we find these weights wij, then we proceed to do the low dimensional embedding. We find coordinates in low dimensions y such that each yi is still approximately equal to wij yj summation. And so in other words, this local property of each xi originally being expressed as a linear combination of its neighbor, all its neighbors, is preserved in the low dimensional embedding. And that's the second step of LLE. So now let's look at the derivations. We'll look at the derivation of the first step, and then we'll look at the derivation of the second step for one-dimensional case, and then we'll extend it to the multidimensional case. So the first step is called local linearization. Here we are given the high-dimensional coordinates xi's of all points, all sample points, and our goal is to find the weights wij, where I and j are neighboring points. Okay, so we have to express xi as a weighted sum of its neighbors xj. In other words, xi is approximately equal to summation over all samples in the neighborhood of I, which is n sub I, wij xj. And this shows schematically how each xi is a weighted combination of the xj's. Now, these weights must satisfy two conditions, actually one condition. Summation j wij should be equal to 1. In other words, so this is xi, a sample point xi, and this is xij. So you have, if this is point 1, then this is wi1. If the sample is 2, then this is wi2. This is wi3, this is wi4, and so on. So wi1 plus wi2 plus wi3 and so on, all the weights that are connected to xi, they should add up to 1. And this property should hold for every sample xi. So this xj has its own neighborhood. It would be connected to some other points here. And so if you take the sum of all these weights, again, it should sum up to 1. Now, why is this requirement there? This is because of two reasons. One, translation invariance. So if I replace each xi with xi prime equals xi minus s, where s is some vector, this s is any vector, then xi prime is approximately equal to wij xj prime. In other words, if I take all these points, xi, xj, all these points, and I shift them by an amount s, this s here, then the shifted points also will display the same relationship. Xi prime will again be equal to the same weighted combination of the xj primes. So that's called translation or shift invariance. And the other reason is rotation invariance. So if I replace each xi with xi prime equals uxi, where u is a unitary matrix, in other words, a rotation matrix, then again the same property is preserved. Xi prime is approximately equal to the linear combination wij xj prime. So if I take all these points and then rotate the x-axis, y-axis, all the axes, the points remain the same, the axes change. So now the coordinates change of the points. So each coordinate xi is now xi prime, which is u of xi, where u is determined by the amount of rotation. And so again, even after the rotation, this same property holds. That's rotation invariance. So translation invariance, why does translation invariance happen? When wij summation over all the neighboring points is equal to 1. So we have originally xi is approximately equal to wij xj. Now let us shift all the points. So now each xi is replaced with xi prime, which is equal to xi minus s. Same with all the points, the same s. So every index I, xj will be xj minus s, x1 will be x1 minus s, x2 will be x2 minus s, and so on. So all the points are translated by the same amount, s. So now let's look at what happens to wij, the same weighted sum of the xj primes. Since each xj prime is xj minus s, so this is what we have. Actually, the parenthesis should be here, which is equal to, now I open up the parenthesis, so it is equal to summation wij xj minus summation wij s, which is equal to, now the first term is approximately equal to xi. This we assume to be true. This weighted sum of the xj's was equal to xi, because this is not translated. These are the original xj's. And the summation wij is 1. And s is a constant, whence the second term is simply s. So the first term is xi and the second term is s. So that is equal to xi prime. So what we just showed is that if summation wij is 1 and xi is expressed as a linear combination of its neighbors, xj's, with wij's being the weights, then the same relationship holds for xi prime. Xi prime is equal to summation wij xj prime. So our goal is now to minimize xi minus summation wij xj. This is a vector, so we take its L2 norm squared, which we want to minimize, and subject to this constraint, summation wij should equal to 1. Now, since summation wij equals 1, I can take this inside this summation. This first term in this summation is summation wij xi, and since xi is constant with respect to the summation, it's equal to xi times summation wij, but the latter, summation wij, is 1. And so clearly this is equal to this expression here. And now I replace this constraint, which was a summation wij, with the vector form of the same constraint. So wi is a weight matrix, and that consists of wi1 through wik. These are the k nearest neighbors of xi. And so the dimension of this vector wi is k by 1. And so we have to minimize this. Now, I let this matrix Zi be equal to x1 minus xi up to xk minus xi. Now, this one until this k here, these are not the actual indexes of the sample points. I just used this numbering 1 to j here and k here simply to denote the k nearest neighbors of xi. Okay, this is not, once again I repeat, this is not the actual sample indexed 1. This is not the sample indexed j, and this is not the sample indexed k. These are the k nearest neighbors of xi, which I have renumbered in another way. Okay, and so from each of these neighbors, I subtract xi. And so that gives me this matrix Zi, and since each of these sample points is d-dimensional and I have k nearest neighbors, so this is a d by k matrix. And observing that each each column of this matrix Zi is of this form, this can be replaced with Zi, and if we remove the summation, and likewise this Wij can be vectorized, giving rise to this expression here. So this double summation, it's not a double summation, this summation is actually equal to the L2 norm squared of Zi matrix times Wi vector, which is equal to Zi Wi transpose times Zi Wi. And Zi is because I have xj minus xi in this summation here, which, if I open this transposition, I get Wi transpose Zi transpose Zi, and I define Gi to be Zi transpose Zi, whence this expression gives me Wi transpose times Gi times Wi. Now, this Gi is a k by k matrix because Zi is d by k, so Zi transpose is k by d and Zi is d by k. So this gives a k by k matrix, and each element of Gi, this matrix, is of the form xj minus xi transpose xj minus xi. So it is a, it's of the form xj minus xi times xk minus xi in row j and column k. So it is, in fact, a gram matrix. It's not the normalized gram matrix where everything is shifted according to the mean. It's another form of the gram matrix, and it's local to this point xi. That's why I call it a local gram matrix. And that is the same as this Gi here. Whence I have to minimize this Wi transpose Giw subject to this constraint. Wi transpose 1 equals 1. So this is what I land up with. I have to minimize Wi transpose Giwi subject to Wi transpose 1. And so what's the solution to this constraint optimization problem? It's given by this expression here, and this can be derived readily using Lagrangian. And so this is the expression for Wi here. Wi equals Gi inverse 1 divided by 1 transpose Gi inverse 1. And I have to apply this operation for every point xi. And then I get my wi's. What are the wi's? The wi's are weights such that summation wij xj is approximately equal to xi. So I am expressing each xi as a weighted combination of its k nearest neighbors. That ends the local linearization step. So this is the step 1 of the LLE algorithm. What we do is we have our n sample points. Now for each sample point, this is what we do. We find the k nearest neighborhoods of xi, which is given by ni, and the crudest method to do that without using any complex data structures is to find all pairwise distances and then sort them and find the k nearest neighborhoods. So then I find my zi, where I take all the nearest neighbors of this sample point xi and I subtract xi from each of them. That gives me my zi. And then I obtain the local gram matrix around point xi, which is zi transpose zi, and then this gives me, this expression here gives me the weight wi. This is the first step of LLE. So local linearization is complete at this point. We'll move on to the next step, that is low dimensional embedding. So at this point, we have the weights, and we don't really need any xi at this point. We already have the weights, and that's all that we need. And so this is what we will retain. Of course, xi's are inputs, so it's just that we don't have any need for them anymore. So now let's move on to low dimensional embedding. At this point, the weights have been determined already, and let's fix the weights. We won't change the weights any longer. And now our goal is to find the low dimensional coordinates yi, where I is a sample and yi is the n-dimensional coordinate vector corresponding to the same sample point I. So when we find y, we have to make sure that this expression is valid. So yi should be approximately equal to summation of wij, yj, where yj's are in the neighborhood of sample I. So at this point, let's define a weight matrix, n by n weight matrix. We already have the wij's. What are the wij's? How are they defined? Now, wii is 0. So you don't have a weight for a sample to itself. It's only the sample and its neighbors, j. So wij exists, it's non-zero, when j belongs to the neighborhood of I. And when j does not belong to the neighborhood of I, wij is again equal to 0. So this is our weight matrix, and it is a n by n matrix where n is the number of samples. So we have one row for each sample, and this is row I, so it corresponds to the ith sample, xi. Now, we have how many entries in this row? We have n entries because it's a n by n matrix, so it has n columns. And out of these, most of the entries will be 0. And that includes the diagonal, because if this is row I, the diagonal element corresponds to column I, so this is WII, and that is 0 because we want Wij to be 0 when j equals I. And it's 0 everywhere else except in the columns corresponding to the neighborhood Ni of sample I. So it's only these points where the entries of this W matrix will be non-zero. And how many such non-zero entries shall we have? K, because K is the size of each neighborhood. And moreover, when we add up all the non-zero entries, we should get 1 as the sum. Why? Because summation Wij should be equal to 1. In other words, when we take any row like this and add up all the elements, then we should again get 1. In terms of vectors, what that means is if we multiply this matrix W with a vector of all ones, then we should get all ones. So this is what it means. Since summation Wij equals 1, W times 1 should equal 1 because the sum of each row, all the entries in each row add up to 1. That's why. Okay, so now we define the weight matrix, and now let's define the coordinate matrix. This coordinate matrix is Y, uppercase Y, and each row of this Y is the low dimensional embedding of the samples transposed. So since we have n transpose, each row corresponds to a sample, and we have n samples, so this number of rows is equal to n, and we are looking for lower m dimensional embedding. Therefore, the number of columns here is m, this m. So this is a m by m matrix Y, and it's to be determined because we have not yet found out the coordinates of the sample points in low dimensional space. Now, since we have to determine all the entries of this n by n matrix Y, we have n times m number of variables. And how many constraints we have? We have one constraint, or one equation to satisfy rather, which is per sample point, which is yi is equal to summation of wij yj. So we have more variables, scalar variables. Each element, each entry of this matrix Y is a variable, and we have only n number of equations to satisfy. So in other words, we have more variables than equations. That's why we can place more constraints so that we get a unique value of y with those constraints. So what are the constraints? One, we shall assume that the coordinates are centered at the origin. That's one constraint. In other words, y transpose 1 should be equal to 0. Then we also can impose this constraint, y transpose y equals ni. In other words, if we take since it's already centered at the origin, so y transpose y, if you divide it by n, then that gives us the covariance matrix. And we want to impose the constraint that the covariance matrix is equal to the identity matrix. Why so? The answer to the both questions is, think about PCA being applied to the y's. So if you had any, just pretend, ignore this LLE. If you have points in m dimensions, whose coordinates are the y's, and you apply PCA to it, then the covariance matrix will be a strictly diagonal matrix. Now, if you appropriately scale the axes, the principal components, then the covariance matrix will turn out to be the identity matrix. In other words, that would mean that all the points are scattered around a sphere. They're not like an ellipse or something. So that's what it means. So these are the two constraints that we shall impose on our problem. What are the two constraints again? Y transpose Y equals Ni. In other words, the covariance matrix should be equal to the identity matrix, and the coordinates should be centered at the origin so that Y transpose 1 equals 0. And this is our problem. Objective function is to minimize this summation. Summation over all sample points of yi minus summation wij at yj. And since we have n number of terms, one term in this summation per sample point, let's call that term phi of yi. And so phi of yi is simply this term, which is the squared Euclidean distance, or rather the squared 2 norm, and that's equal to yi minus summation wij yj transposed times yi minus summation wij yj. Hence, phi of y, what we want to minimize, the objective function is equal to summation I phi of yi. Now, for simplicity, let's first focus on one-dimensional embedding. So we will look at when n equals 1. Now, the objective function is phi of y, where y is now a vector instead of a matrix, because we have each sample point now representing a scalar. yi is a scalar, and so our objective function is summation I of yi. This is now a scalar because we are looking at one-dimensional embedding, minus summation of wij yj norm squared. And this is the objective function, and each term in the objective function is phi of yi, which is defined in this manner: yi minus summation wij yj transpose. Actually, we don't even need the transpose here because it's simply this times this itself. So it's this expression squared, which implies that phi is equal to summation of phi of yi, which now let's simplify. We plug in the value of phi yi here using this expression, and then this, if we multiply this with this, we get yi squared, and then yi multiplied by this summation with a negative sign here, and this yi multiplied by this summation again with a negative sign gives us, this should have been a negative here, 2 times summation yi wij yj, and this double summation is here is the product of this summation and this summation. And this can be vectorized as follows. So the first term is y transpose y. The next term is negative 2y transpose wy. And the third term is, the double summation is wy transpose wy. So let's say that phi of y, which was now this expression, is equal to y transpose my. Then M is defined as this matrix here, I minus W transpose I minus W. So if M is equal to this expression, then phi Y is equal to Y transpose times I minus W transpose I minus W times Y, which reduces to this expression here. So that's our simplified objective function in case of one-dimensional embedding. And it's a quadratic Y transpose My, where our matrix M is defined as I minus W transpose I minus W. So this is what we have as our constraint optimization problem. Minimize phi y equals Y transpose My, subject to this is the constraint that comes from the covariance matrix considerations, Y transpose Y equals N, and this second constraint, Y transpose 1 equals 0, comes from the fact that we want the points in the reduced dimension, in the one dimension, to be centered around the origin. Now let's have a look at the spectrum of Y. The spectrum of M, sorry. So the spectrum of M. Since M is I minus W transpose I minus W, so it's some matrix transposed times that matrix, it is obviously symmetric, positive, semi-definite. Now W1 equals 1. We know this. How? Because summation of the weights along each row of our W matrix should add up to 1. We know that. Summation Wij equals 1. From that we get this expression, W times 1 equals 1. Now let's take this M here, which is I minus W transpose I minus W, and post multiply it with this vector 1. What happens? Now, if we multiply this I minus W times 1, we get I times 1 is 1 and W times 1 is this. But since W times 1 is 1, this I minus W times 1 is equal to 0, whence this expression is equal to 0. So M times 1, since I minus W transpose I minus W here is nothing but M, what we see is that M times this vector 1 is equal to 0, which is the same thing as 0 times the vector 1. And this fits the definition of eigenvalue, eigenvector. So 1 is an eigenvector of our matrix M, and the corresponding eigenvalue is 0. And since it is positive semi-definite, all the eigenvalues are non-negative. So the smallest eigenvalue is 0. And since we sort the eigenvectors and eigenvalues such that the smallest eigenvalue comes last and the largest eigenvalue comes first, we automatically know that lambda n, the smallest eigenvalue, is 0, and the corresponding eigenvector of M is Vn, which is 1. So that's our smallest eigenpair of the matrix M. Okay, so now from spectral decomposition, how do we do this minimization? This, we obviously cannot let y be equal to 1, because then what would happen? All the points, if this vector y, if we let it equal to the eigenvector Vn, which was equal to a vector of 1s, that implies that all the points, all the sample points would be placed exactly at the same coordinate 1, because we are looking at one-dimensional embedding. So we have to disallow this. And that is automatically imposed by this constraint. Y transpose 1 equals 0. And since all the eigenvectors are mutually orthogonal, so since 1 is one of the eigenvectors, the y's could be the other eigenvectors or a linear combination of the eigenvectors for that matter. So they have to be orthogonal to the smallest eigenvector of 1. And so our solution is y equals Vn minus 1. So we take the second smallest eigenvector, Vn minus 1. And that gives us the coordinates y in our one-dimensional embedding. And what would be the value of y transpose my in that case? Since we want to minimize it, lambda n minus 1. Now, we know that each eigenvector is a direction, and usually it's normalized so that the eigenvector is a unit vector. However, here we need y transpose y equals n. So we have to scale the eigenvector so that this constraint holds. V transpose n minus 1 times Vn minus 1 should equal n. In other words, the norm of this eigenvector should be square root of n. Now let's move our attention back to m dimensionals. So far we were looking at one-dimensional case. We saw that we should take the one-dimensional coordinates y to be the second smallest eigenvector. Now we can easily see what will happen in the m-dimensional case. So now this is what we have to minimize, the trace of y transpose my, and where m is given by this expression here, and the constraints are, from the covariance matrix considerations, we have y transpose y should equal ni, and from the fact that we want the coordinates to be centered around the origin, we get the other constraint, y transpose 1 equals 0, which, by the way, automatically makes all the columns of this matrix Y orthogonal to the smallest eigenvector 1. So our solution is we take the smallest n eigenvectors excluding the n which is all ones. So we drop the smallest eigenvector Vn, and then Vn minus 1, Vn minus 2 up till Vn minus m. We take these as the columns of our matrix Y. And we again need to scale each of these eigenvectors, each of these columns of Y, so that V transpose V should equal n. So each of these columns has a Euclidean norm of square root of n. And that's our solution to the embedding problem. The algorithm. We've already seen the first step of LLE. This is what we do. The high dimensional sample points, n sample points altogether, are provided, and we then find Wi around each of those sample points. And then that helps us create this W matrix. Now this is only, you know that it's not really equal to each row of this is not really equal to Wi transpose because you have so many zeros in it, but I've just used this expression just so that you know that you have to extract the weight matrix W. And then we construct M, which is I minus W transpose I minus W. then we do spectral decomposition of M to get our smallest eigenvectors, excluding the very smallest one. And that gives us this matrix Y, low dimensional coordinate matrix. And Y1 up to Yn will be the different low dimensional coordinates of the sample point. So we have to take, for the first sample point x1, we have to take the first element of Vn minus 1, first element of Vn minus 2 until the first element of Vn minus n, and that gives us the set of coordinates for this sample point y1, and so on. This is the second step of LLE, the end.